Okay. Good evening, everyone. Welcome to the class of GEH 1036 and GEK 1505. Are all of you coming from School of Computing? I randomly checked 2 persons. They are from School of Computing. How many of you are from engineering? Science? And arts and social sciences? Okay, good. So anyway, this is the first lesson. I have to introduce myself. My name is Yang Yue here. My office is at S17. It's a separate building in Faculty of Science, where mathematics department is located. My office is 0705, 7th floor, room 5. And here's my email, office phone number. Okay, so feel free to contact me if you have questions. Today is 14th of January. It happens to be, I think the United Nations just recognized today is so-called Logic Day, the Day of Logic. Anyway, so let's start the lecture. Because it is the first lecture, I'll spend some time to do a short introduction. And after that, we'll get into business. So we are going to talk about some topics related to mathematics and money and financial things. So in particular, we'll talk about interest and something called annuities. Okay. Okay, so let's say the most important thing first, right? How your grade is going to be determined. So the grading policy is, so 30% will be based on 2 online quizzes. I'm going to give you details later. Most likely, one will be given before the break and one, I don't know, somewhere in the second half. Okay. We will not have midterm. Last time when I taught this course, I had midterm, and somehow it's very hard to manage. The class size was big, and it's not easy. There are lots of makeups and so on and so forth. So to make life easier, we'll just have online quizzes. Okay, it's like 2 homework assignments, and then you'll be graded by machine, and this determine your 30% grade. And then we'll have a final exam. So this will count it 70%. It's closed book, but you can bring 1 help sheet. The exam date is already scheduled by the university, so it's 2nd May. It's a Saturday in the morning. Okay. Okay, any questions? Is it clear? Okay. Okay, all lectures will be webcasted. It will be posted on the Luminous site. So on the Luminous, probably now you see three courses related to this GEH. Please go to the one which combine the GEH and GEK. I'm going to delete the other 2 in a week time, right? So we only need 1 because there are so few people take GEK. So please go to the joint website of GEH and GEK, and then you'll find the material of this course. Okay. Now I want to say, I encourage you to attend lectures. Okay. So actually, I don't care. For my lecture, so I encourage you to come to NUS, not just for my lecture, right? So I don't care how you learn this stuff. You can learn it at home, you can learn it on beach, I don't care. But I do encourage you to come to NUS. So because I find recently there's a trend, it seems people do not want to go to campus. I think it's a mistake, right? So you may not like my course, or you may not like this, you may not like that, but there must be something you like, right? I believe the university have a very vibrant cultural life, right? You should come to university to have communication with professors, with your fellow classmates, and I believe NUS is one of the best university in the world or in Asia. So there are lots of exciting activities, talks, and lectures. So even you don't like my lecture, you should find something you like, right? So don't waste your time, just stay home and just hang around with your friends. But you can, but there are so many other opportunities, right? Don't miss them. Okay, so I encourage you come to school and join the community, right? So this is my message. And one word about this webcast, right? So sometimes the attendance was dropped so low that it, how to say, is very dangerous, to a dangerous level. So, so I want to say, although I don't care whether you attend or not, but if there's no audience, I will not give lectures. I think it's fair, right? If nobody was sitting here, I won't speak to the empty room. Okay, so then you won't see any webcast. Okay, so that's the deal. Okay, but okay, so I don't believe that I will have no audience. But just in case, in the unlikely case that there's no audience, I will pack my things and go home. Okay. All right, and also do give me feedbacks. So this course, because the audience are coming from different backgrounds, right? So there are people from School of Computing, there are people from other faculties. So it's very hard to how to say, to entertain everyone. So hopefully you can give me feedbacks so that I can adjust. Maybe I'll try my best to fit your interest. Okay. All right, so the references for the book, for the course, I think it's better you just read the slides, or I'll provide the slides and tutorial problems on the Luminous side, okay? And okay, so the tutorial will be starting from week 3, as you know. Now, traditionally, there's okay, Professor Leung was the person who designed the syllabus, so he has this book. Now I don't know whether it's 3rd or 4th edition. So there's several editions of this book. Lots of material was based in my lecture will be based on this book. And some tutorial problems also are taken from this book. But there are quite a number of topics are new, outside this textbook. For this, the second reference, I only use chapter 1 for the first week. So I only take the part which related to money. So I already put that chapter in the Luminous site. So if you want to have a good reference of today's lecture and Friday's lecture, please read the material I upload in the Luminous site. Okay. And the rest of the book, you can read it if you want. Right? Okay. Questions? Now, so what are the objectives? Okay, so the objectives are So we want to exhibit some simple mathematical ideas applicable in everyday life. Right? So we want to teach you some mathematics, and these mathematics are related to everyday life. And in the process, gain an appreciation of the beauty and power of mathematics. So I hope I can achieve that. This is very difficult, but I hope I can achieve that. So the topics are, so today, this week, we are going to talk about the first one, and then we'll move on to these topics. Okay, so I will not read the item by item. You will see. Okay, so when I look at NUS mod, I find that there's a comment by this person, Mario Lorenzo. Does any of you know him? He was taking the course, but I didn't see him. So, okay, but I think his comments are quite nice, so quite interesting. So maybe more accurate, right? Because he's a student, so from student point of view, his comments will give you more information. Okay, so maybe you have read it, but let me use this opportunity to repeat his message. Okay, if you know him, tell him I'm repeating his message. Okay, he was saying that this module is a general education module offered by the Department of Mathematics to satisfy the human and cultural pillar, right? So we have for the general education module, we have 5 pillars, and somehow this is one of the to satisfy one of the pillars. Okay, so the module comprises of mathematical concepts in real life, in real life application, like financial mathematics, logic and basic set theory, combinatorics and probability, voting systems, fair division, graph theory, and cryptography are covered in this module. Okay. However, students who are strong in math may find this module too superficial, like those from computer science, SOC, okay, since it only covers the basic of the concept. That's, okay, I don't like this, but probably it's true, so I have to, it's not too deep, because of, this is general education, right? So the syllabus was set that way. Okay. If you want to go deeper, take courses in math. Take something with MA, okay. And then, okay, he has some comments on me. So I guess, okay, so I want to emphasize the even though part, right? So his pace is slow. Okay, now probably getting slower. And speaks with accent, probably is getting worse. So anyway, so that's, I think it's accurate. Okay. Then he delivers the concept, okay, systematically. I hope I can do that. So he's open to any questions. Indeed, I'm open to any questions. So if you have questions, please stop me and ask. And okay, so I hope I can do this, responsive for questions. He usually displays some queries submitted by students in the next week lecture slides. Yeah, so because not all of you will attend the lecture, so I receive email saying, I don't understand this slide, so please, so if you have those questions, please email me, so I'll respond to your queries at the next lecture, okay, or face-to-face if you want. Okay, so that's, okay, so then he was commenting on the exam, the level of exam. So because this year is different from his year, so I modified this part. It's not literally word by word of his code. Okay, so he says the level of the questions, I add this in the exams. Originally, he was commenting on midterms and exams, but we don't have midterms. Okay. So he said not too high, since this is general education module, where there are students who do not have strong, okay, so, right, because different people have different background, right? So this is general education, so he was commenting the level of question is not too high. Okay. It's, again, probably true. Depend on your background, okay. And, okay, so no consistent effort is needed. I strongly disagree with this, but but this is what he said. Okay, So I did not come to lecture and tutorial after midterm. Actually, I don't remember him at all. So, so maybe he's polite, but maybe he disappeared after first lesson, or I don't know. Okay, and studied for the final around 1 week, probably the exam days. Okay. So my comment is, I don't encourage you to do this, right? Of course, this is a free country. You can do whatever you want to do. Okay, the last part I think is also important. So he said lectures are actually webcasted, so I did not watch, but I did not watch it since most of the contents are already written in lecture notes. That's probably true also, right? Okay, so this part I want to emphasize. Right? However, beware of the steep bell curve. The reasons are the level of questions are not set too high, so he was saying that right, it's not too high. And also many math and CS students taking this module to get their free A's. Okay, so I think this steep bell curve part is true. Okay, if you think you can get almost full marks, well, so are the 300 of your classmates also think the same thing, right? So in the end, well, it's not so easy. So this free A part is completely false, right? Don't believe me. Okay, so because we cannot give everybody A, you please take this steep bell curve into consideration, because some of you think you can get free A's. It's not the case. Okay, so I have no choice, right? I have to in the end, probably it's a machine who is going to mark your exam. So if you make mistakes, then it's mistakes. So okay, so I guess that's all quotes from Mario. Questions? I hope the message is clear. I think his comments are mostly accurate. Okay. All right. Can we move on? Sorry? Is there negative? What is negative marking? No, I don't think so. Okay. Any other questions other than negative marking? Okay, so now we start the proper lecture, right? We are going to talk about some problem about money, but related to mathematics. Okay, so let's look at one example, simple example, right? So this to get things started. So the question is, suppose you put $100 in a bank, and then the annual interest rate is 5%. Okay, how much do you have after 100 years? Suppose you live long, right? So after 100 years, how much do you have? Okay, so this is a question. Right? Now the question is not, okay, so it's ambiguous. It's not clear, because it depends on how the interest is calculated, right? In real life, especially in the lecture in first week, there are words coming from real life, like interest or some other things. So it's not mathematically defined. So people use it in different contexts. The words probably mean different things. So that's we have to be careful about this. So sometimes people try to cheat or try to do things, try to take advantage of this ambiguity. Okay. Anyway, so here, although I give you the number 5% annual interest, it's not clear how you calculate this, right? So, in other words, is the interest. So there are two typical ways to calculate interest. One way is called simple, the other way is called compound. Okay, so now let's see what are the two ways. Okay, for the simple, to calculate interest in the simple way is It goes like this, right? So it's 5%, right? So every year, so you deposit 100. So after 1 year, you get $5 interest, right? So this is, everybody agree with this. This is the meaning of interest rate. So you will get $5 interest each year. Now, in the simple way of calculating interest, so over 100 years, you will get, okay, every year you get $5. So 100, in 100 years, you get 100 times 5, right? So you get $500. So this is the simple way, right? Okay. So you will get the answer for the question was $600. Okay. Now, but in real life, simple interest is seldom used. I was told like this. So in the past year, people from business school, some of the students are from business school. They confirmed indeed this is the case. They never use simple interest rate. So the interest rate was calculated. They use a compound interest rate. So because after 1 year you have this amount, right? You have $105. So the extra 5 should be considered, right? So it's the interest will be considered upon interest upon interest. So getting higher and higher. So let's see. Suppose we take this compound way. What is the result? Okay, so let's consider this compound interest. So if you have, so in general, right, so if you have S dollars at the start of the year, then at the end of it, you will have, okay, so this amount, right? So at the very beginning, you have $100. After first year, we know that we have 105. This is okay. Now, after 2 years, so you have to use this amount multiply whatever you have at the end of the first year, right? So this is the formula tells us, right? After 1 year, you get 105. So you have to use this number times, now S equal 105, right? Now 105, if I substitute this back, I get this number, 1.05 squared times 100. This is after 2 years. Well, you are NUS students. I don't need to give you more examples. So you just keep doing this. After 100 years, you'll get this number raised to the power 100, right? Multiply this one, the amount you deposit. So surprisingly, you get this large number, 13,000, right? After 100 years. So there's a big difference between 600 and this number. It's quite big, significantly big. Right? So, okay, so from now on, okay, it's not always, but in most cases, interest rate means compound interest rate, especially in the remaining slides of the lecture. Okay, questions? I hope the example is clear. Okay. Okay, so now we state the same thing in a more general terms. They call it mathematician disease, right? Mathematicians always push things into the most general case. Okay, so let's see. So suppose, so the proposition says, if you invest C0 in dollars, it's like you deposit $100. Yes, this is a general statement for that. With an annual compound interest rate of alpha. So alpha is, in the example, it was 5%. The interest rate is 5%, right? Then you will have this, okay, after n years, you will have 1 plus alpha to the power of n times C0. So let's use C sub n to denote the amount of dollar you have after n years. So the formula given by the proposition is C sub n equal this bracket 1 plus alpha to the n times C0. Okay, so the reason is exactly like the example, right? In the example, here is 100. This is, n is also 100. and then the alpha is 5%, right? So, so the proposition is just the same thing as the example, but stated in a general terms, using letters instead of concrete numbers. Okay. So note that this alpha is often written in a percentage, 5%. Actually, it's 0.05, right? So, but usually the rates, interest rate usually is written in percentage, like 5%. Okay, so now look at this equation or formula again. So there are 4 parameters, four letters, different letters. So one is alpha. Okay, so there are 4 parameters in the proposition, namely C0, the original investment, right? So the invest C$0. So this is one parameter. Now alpha, the interest rate, is another parameter. And n is the number of years, is a third parameter. And then you get Cn. After n years, what do you have? So this is the 4th parameter. So you have 4 parameters. Now the typical question, so in the remaining of the lecture, we are going to do this. So usually we are going to give you 3 out of 4 parameters and ask you to get the last one, the one, right? So the typical question are to find the 4th one, assuming you know the other 3. Okay, so actually the example I give you is one of those questions, right? But it's more straightforward. So you know C0, you know alpha, you know n. We ask you to find Cn, right? We know the parameters on the right-hand side. We want to know the parameter on the left-hand side, right? So that's one of the instances of these. Now, in the next slides, I'm going to give you something different and ask you to find the only unknown in the equation. Okay, so let's see how it was done. So here's the variation. So the question is, when will your fortune double in the above scenario? Right? So you deposit something. I ask you after how many years you will double your fortune. Right? So $100 become $200. Right? So okay, so now let's do it slowly. So we want to find n. Right? So assuming we know C0 and alpha, so because in the above scenario, C0 and alpha is given. Right? So we want to find n so that the C sub n is double the amount of C0. Right? So in other words, we are looking for this parameter n such that this Cn equal, how to say, Cn is 2 times C0. Okay, but Cn, the formula is given like this. Right? The left-hand side actually is Cn. So we are looking for n which satisfies this equation. Okay. So in other words, for which n it satisfies this formula. Here, this Ln is the natural log. There are a few mathematical terms appear in the slides. I'm going to, if this is the first time you see this, treat it as log, just like log. Okay. So I will explain this, the property of this log function in future. If you never see it before, don't worry. It will become clearer. Okay, so let me repeat the question. We are looking for n which satisfies this equation. Okay, and alpha is a fixed number. Is 5%. Okay. Okay, so okay. So I thought we have this. Okay, anyway, so So now we are looking for this n. So let's look at some fact about this log. So here's a fact about this log, which claims when x is small, the log 1 plus x is more or less same as x. All these mathematical facts will be explained later. So let's first continue with the calculation and then worry about the mathematical facts involved. For those from school computing, probably you know this very well. Okay, so in other words, when alpha is small, n is more or less, okay, you move this thing to the right? But the log, by the property of log, this is more or less just alpha. So it's more or less n is log 2 over alpha. Say alpha is 5%, so you convert 5% into 5 over 100, right? So this is just saying that. So the n is more or less, if you punch your calculator, you get this number. Okay, so n is more or less this 69.3 over, in our example, this is 5. Okay. Now, because this number is a very funny number, so we don't like them, people usually round it to 72. The reason is 72 has lots of factors, so it can be divided by many, like 3, 4, 6. Unfortunately, it cannot be divided by 5, but no. Okay. In the reference, there are more discussion about this 72. So it is called the rule of 72. So somehow people working in real life in the bank have this so-called rule of 72. It says, okay, so I don't need this. At annual interest rate of beta, it takes about 72 over beta years for an investment to double. Now in our case, this is 5. Okay. So it's take about around 14.4 years to double. Is it okay, the example? Now you can replace investment to debt, right? Suppose you own this debt, the interest rate is so and so, then after so many years, how much debt do you own, right? So you can, I mean, there are lots of things like this, lots of calculations like this. Okay, so now I want to make a comment on this simple interest rate and the compound interest rate. So this actually is not restricted to financial math, right? For example, people from SOC, when you study complexity of an algorithm, this contrast was very, very important, right? It's between feasible and non-feasible, right? Okay, so so here I want to introduce two terms. One is called linear growth. The other one is exponential growth, right? So the message I want to say is exponential growth is much, much faster than linear growth. Okay, so let us recall the difference of this investment FT after time t under a simple interest rate against versus compound interest. Okay, so this simple interest was calculated this way. It's more or less like a line, a linear, right? So it's a plus some constant times t. T is the time, right? So this is so-called linear growth in t, because I think you know that if you plot this on a computer, it gives you a straight line. So that's linear, right? Now for compound interest, the growth is not like this. So it's some constant times another constant to the power of t. Just now, like c is 1.05, right? So c usually is bigger than 0, right? So the growth is calculated like this. So this function, c to the t, is called exponential function. So this, the growth is referred as exponential growth. Okay. Now the mathematical fact is exponential growth is much faster than linear growth. Just now, in our example, after 100 years, the linear growth is 600, right? But the other one is 13,000 or something. So the difference was big. Okay, so that was the first variation. So now we want to give another example, see another variation. Okay, so sometimes the interest rate was given not yearly, not year by year. Sometimes you are given an interest rate like monthly or quarterly or something else, maybe daily or, okay. So how to convert one from the other, right? So this is our next question. Okay, so let's look at the example first. Okay, so the example says consider a loan of amount C with an interest rate of 2% compoundedly quarterly, right? So the important thing was quarterly. So how much do you own after 1 year? Or in other words, what is the annual interest rate? Suppose the quarterly interest rate was 2%. What is the annual interest rate? Right, that's the question. The wrong answer was because quarter is 1/4, right? So you just multiply 4, and then you get 8%. So this is a wrong answer. Actually, it's more than that, right? So the correct answer was using our formula, the proposition we just derived. So it's 1 plus alpha, which is 1.02. Now the alpha is 2%. So this number raised to the power of 4 times c, so you get actually is 1.08 with the actual 2.4 afterward. So it's more than 1.08. Okay, right? So conclusion is such a loan has annual interest rate of 8.24 percent, rather than 8%. Okay, so the rate of this is called the annual percentage rate of the loan. Okay, okay, so simple enough, right? If you know the formula is just the same variation, the variation of the same thing. Okay. Okay. So now let's do one more, right? So just now we convert the quarterly interest rate to annual interest rate. Now let's convert annual interest rate to monthly interest rate. Again, it's the same thing, more or less the same thing. So let's see. So the example says if a loan has an annual interest rate of I, right? What is the monthly interest rate alpha? This example will be used in further examples. So the solution says the alpha and I are related by this equation. Do you agree? So, for example, you see suppose you deposit $1, right? After first month, you get 1 plus alpha, right? After second month, this raised to power of 2. So after 12 months, you get this amount. Now suppose the annual interest rate is I, you deposit $1, after 1 year you get 1 plus I, right? So these two should be the same. 12 months is 1 year. So the alpha and I are related by this equation. So in other words, this is like you take the roots and you get this. Well, I don't know. So in the textbook it makes this remark. So sometimes in a bank people try to do funny things, but I guess this is less mathematical. So allow me to skip this. It's not important. Okay. Okay. So now let's look at Okay, so this example after example after example. It's all use that same formula, right? You'll see the same thing over and over again. Maybe that's why Mario said I'm slow. So it's slow, it's like this. Okay, so let's try. So now we want to solve this problem. So you are given two options. Invest $1,000 now, or take $1,100 in 2 years' time. What annual rate of investment returns? Okay, so suppose the annual interest rate is alpha, right? So what alpha would make the first option more attractive than the second? Right? So you are given two options. You know the interest rate, right? So either you deposit $1,000, then based on the interest rate, you calculate after 2 years what do you have, right? Or you have another option, you get $1,100 in 2 years, right? So which option should you take? Right? Of course, it depends on alpha. If alpha is 0, then certainly you don't take it, right? So if alpha is huge, then you take it. Right? So, okay, so let's see. So how do we do this? Well, you just calculate based on alpha, how much money do you have after 2 years, right? So this is, okay, under option 1, that is, suppose you invest now, you will have this amount after 2 years, right? So this is the same formula appear, 20 times, right? Something like this. Okay, so this question becomes, we want to compare this number with 1,100 to see for which alpha the option 1 is more than or at least equal to option 2. Okay. And then you can punch your calculator, solve. So the answer from textbook says if alpha bigger than this number, 4.88, you can consider. Otherwise, you lose money. Okay. Is this okay? Questions? Okay, so another example, another variation. So we can reformulate the problem as this. So what is this amount, $1,100 in 2 years' time, worth today? Right? You are promised to get this amount in 2 years' time. Now, what is what is it worth today? Right? So more generally, okay, I'm going to replace these concrete number by alphabets. Right? So what is having X dollar in K years' time worth today? Right? This is the same question, but in a more general setting. So assuming the rate of investment return is I. Just now the I was 2%. Okay, so in terms of the proposition, we want to find C0, assuming we know Cn, n, and alpha. Right, so this is, we know the 3 parameters, alpha, interest rate, n, the number of years, and the value at the end of the nth year, Cn. We want to find what is the current amount, C0. Right? So we know these 3 parameters. We want to find this one. Okay. Well, just look at the formula again. Right? So Y dollars today will grow to this amount in K years' time. Right? This is the same formula, same proposition. Okay. So setting X equal this amount, you'll see that X in K years' time is equivalent to Y dollars today, right? So you solve this, right? Because Y dollar today will become X dollar after K years, right? So now you know X, you want to find Y. So you move the terms, you get y equal this thing times x, right? So that's the formula. Okay. So in business, this y is called present value of x in k-year time, assuming interest rate of I. So sometimes people use this present value, referring things. Okay, so you can make things complicated. So not only they promise give you certain amount of money after 2 years, they'll say after 2 years I give you this amount, after 3 years I give you the other amount, after 5 years I give you another amount, and so on and so forth, right? So the example is it's just saying that. So okay, the question is, if you are offered amount S1, S2, dot, 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 SR at future years, T1, T2, dot, dot, TR, and assuming the annual interest rate is I, how much is that equivalent to you getting today, right? Okay, so somebody promised you after T1 years give you S1, T2 years give you S2, TR years give you SR. So what is his promise worth today? Okay, so we just use the formula. So we just saw the present value of SI given at year TI is this, right? So this is a formula. This is the present value of x in k years. So you use that. The present value of SI given at year TI is calculated by this. Okay? So in today's money, the offer is equivalent to, so S1 is equivalent to this amount, S2 is equivalent to that amount, and so on and so forth. So it is, you add them up, you get the present value of his offer. Okay. Now I want to introduce a shorthand for these sum. Again, for SOC students, you may see this many times before, but people in the audience are not all from SOC. Okay, so let's see. So I want to introduce this capital sigma. It's a Greek letter for sum. Okay, so in this, I want to write this sum in shorter forms. I'll write it as sigma. I read this as I from 1 to R, right? You see the sum, the index, the subscript of the sum changes from 1, 2, 3, dot, 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 all the way to R, right? So this, the first part of the notation saying I start from 1, right? This is T1, this is S1. So I start from 1, so the I inside the expression, you replace it by 1. That's your starting point. And then you start from 1, you go to the next I plus 1. You go to 2. Okay. So you add S2 over 1 plus I to the power T2. And then you go to I equals 3. Right? So it become, okay, I didn't type, but S3 over 1 plus I to the power T3. Dot, 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 all the way go to R. So the last term you finish at when you reach the ceiling, when you reach this R. You stop at S sub R divided by 1 plus I to the power TR. Right? So this is a shorthand for this sum. You'll get used to it. This is a very common notation in mathematics. Okay. So I want to say a little bit more about this. Okay. So this is a summation. There are some conventions, right? So instead of writing, so suppose you have a sequence. You have several items, right? You want to add them up, right? So you can write them A1 plus A2 plus A3 plus dot, dot, dot to AN. So this is a long-winded way of writing a sum. Now you can also write in a shorthand using this summation, the sigma, capital sigma. So this notation, sigma, I from 1 to n, AI, actually is a shorthand for this. Right? So let me repeat. So if you see I equal 1, this is your starting point. So you start from A1. And then you add the next term, which is A2. Then you add A3, you add A4, until you hit the number on top of the sigma, until you hit AN, right? So this is a shorthand for that sum. Okay. Now, I give you an example of this. So what is this? Sum k from 0 to 12, x to the power of k. So we should, okay, follow follow my explanation. I should start from k equals 0, right? So I should look at x to the power of 0. But in mathematics, there's a convention. Anything to the power of 0 is 1. Okay. So x to the power of 0 is this 1. Okay. And then I'm going to add the next term. So the number after 0 is 1. So I will add x to the power of 1. Right? Then I'll add x to the power of 2 all the way until I add to x to the power of 12. Right? So if I start from 0, actually I have 13 terms. In this example, I start from 1. I goes from 1 to n, I have n terms. But here I start from 0, so I have one extra term. So the sum, actually, there's 13 terms here. Okay. So this is called a geometric series with a common ratio x, because the terms I get is the product, right? So from x you go to x squared, then you go to x cubed, and so on and so forth. This form a so-called geometric series. Now you add them up. So this is the sum of geometric sequence. Okay, questions? Okay, so now we want to look at a slightly more complicated example. So let's consider a rather complicated problem in terms of mortgage, right? So here's the problem 2. Okay. So if you borrow $100,000 at 6% annual interest rate to be paid monthly over 25 years, okay? How much is your monthly payment, right? You borrow this amount of money, and then you give your monthly payment to the bank, right? So how much you should pay every month in order to cancel your loan after 25 years, right? And also there's another related question. How much do you still own after 15 years, right? So these are the really daily life questions. Okay, so we are going to use the same formula. Okay, let's see. So more generally, suppose you borrow C dollars at annual rate I, right? C in this example is 100,000. I in this example is 6%. Okay. Paid monthly over n years. How much is your monthly payment R, right? So in this example, n is 25. So you want to find the number capital R. That is your monthly payment. Okay. So we want to figure out what R is. Is the question clear? Okay. Okay, so first, we are only given annual interest rate, but the payment was done monthly. So first, we have to convert the interest rate from annual interest rate I to the monthly interest rate alpha. Okay. So we have seen this example, we have seen this formula in the earlier example, right? So now the monthly interest rate alpha satisfies this equation as shown in the earlier example. So in our case, we can find alpha. So I is I is 6%, right? So 1 plus I is 1.06. So solving the equation, you get alpha is more or less this. Okay, I don't read this number. So alpha is this number. Okay. This is the monthly interest rate. Okay. So now let's calculate what the capital R should be. Okay. So let us use C sub k to denote the amount owned at the end of k months. Okay. So at the very beginning, you own amount C because that's the amount you borrow from the bank. So you own C. So C0 is C. Right? So after 1 month, how much do you still own? Okay, after 1 month, this part grows with interest, right? C0 becomes C0 times 1 plus alpha, right? So that's why we need this monthly interest rate, right? But you paid the amount capital R, so you have to subtract this amount you paid, right? So after 1 month, you will own C1, which is this amount. Okay? Now, after another month, so in other words, at the end of 2nd month, you still own this amount. Well, the same logic apply here. C2 will be, so after 1st month, you own C1. So the amount of what you own grows with interest. So after another month, this part becomes 1 plus alpha times C1. But you paid another R dollars to the bank, so you have to subtract R again, right? So after 2nd month, you own this amount. Okay. Now, what is C1? So we want to get a general pattern, right? So that's why we unravel this term. So C1 is this funny term. So you replace C1 by this term, you get, okay, 1 plus alpha times, this is the C1. Okay? This is C1, and then this part is still there, minus R. So if you do this, you get C0, which is C, times 1 plus alpha, now you have a squared here, right? Now, this minus R, multiply 1 plus alpha, you get this, minus R times 1 plus alpha. Now, this minus R is still there. So after 2 months, you get this amount. Okay. Now you can try to guess the pattern, right? So continue. We use the same logic. After k months, let's see. So the same logic applies, right? After k minus 1 month, you still own this amount. With 1 more month, this amount grows, becomes 1 plus alpha bracket times this. And you paid R amount, so you minus capital R, right? So CK is 1 plus alpha times CK minus 1, subtract R, right? Now, okay, so you keep unravel the terms. Okay, CK minus 1 becomes CK minus 2, and so on and so forth. But after a few terms, you see the pattern. So it becomes, okay, 1 plus alpha to the power of k times C0 minus R times the sum of these. Well, it's a bit, okay, so does C2 fit the pattern? So what do we get for C2? So it's C times 1 plus alpha to the power of 2, right? So when k equal 2, C sub 2 equal this C times 1 plus alpha to the 2, right? It's like this. When k equal 2, I have a term 1 plus alpha to the power of 2 times C. Now the remaining is this ugly sum. For k equal 2, this is simple, right? So you have a common factor R. Then after you take out, okay, minus R. After you take out minus R, you get 1 plus alpha, right? So here you take a common factor minus R, then you have this, you have 1 plus alpha plus 1 plus alpha square all the way up to 1 plus alpha to the k minus 1. So because of this 1, you have to start from 0, j equals 0. So, okay, I hope you are convinced this formula is correct. If you are not convinced, try to work out C3, and then you'll see the pattern. You work out C3. If you are still not convinced, C4. After C2020, you'll get convinced. Okay. So in general, there's a general formula. C sub k is this. Okay? Okay, so now let's continue, right? Let's continue. So we want to, so there's an ugly sum. We want to find a formula to calculate this sum. But luckily, in high school or in JC, you learn this formula. So the sum of geometric series, actually, there's a formula. So the sum of j equals 0 to k minus 1 x to the j is this. The formula you may learn from j is from 1. But here, what I'm writing is j equals 0. So this formula is correct. Maybe it's slightly different from what you have learned, but it's the same formula. Okay. So if you calculate the sum of geometric series, you get this. Okay. So now let's use this fact. I'm going to justify this fact, give you reasons in next lecture. But let's take it for granted. Continue the calculation. So now the x is 1 plus alpha. Right. So this is a geometric series. X is 1 plus alpha. So x is 1 plus alpha. So you get this, the sum j equals 0 to k minus 1 x to the j is 1 minus, okay, x to the power of k and 1 minus x. But x is 1 plus alpha. So 1 minus x is minus alpha. So I get this one. So therefore, I can simplify this sum, replace this sum by this fraction, right? So c sub k is, okay, 1 plus alpha to the power of k times c minus this term times r. Okay. So now so after loan is fully repaid after n years, that is 12 times n months, we balance the loan. We cancel the loan, right? We completely pay the loan. So the amount you own should be 0, right? After 12 times n months, you get 0. So c sub 12 times n is 0. So plug in the formula, you get, okay, c sub 12n is this, given by the result we just obtained. So 0 should be this. And then you can easily solve r with the subject c. Okay. So you get r is, okay, you move things around, you get this. Okay. So that's the formula. Okay. So in this particular problem, problem 2, what do we have? We have this C is 100,000, I is 6%, and we have calculated alpha. Alpha is some number. And N is 25 years. N is 25. So we use the formula we obtained. We can get R is this. You plug in these numbers, you get R is that. Now, here I said, by recalling, we have a relation between alpha and I, right? So 1 plus alpha to the 12 actually is 1 plus I. So you can actually replace 1 plus alpha to the 12 by 1 plus I. So you get slightly better formula. But unfortunately, you can't get rid of alpha. So alpha is still here. So anyway, you can use this or use that. It gives you the same result. Okay. So in the end, the monthly payment should be this number. Is this okay? Okay. So, okay, let me summarize this example, right? In this example, we use the formula in the proposition over and over again, plus an extra knowledge. We know how to calculate the sum of geometric series, right? Combine these two knowledge, we can calculate the correct amount of R, right? So that's the answer for problem 2. Oh, okay, so the problem 2 have another part, right? They also ask, how much do you own after 15 years? Well, then this part is easy. Recall the formula C sub k, right, after, okay. Remember CK denote the amount owned after k months. So CK is this formula. So you just plug in 15 times 12, right? So after 15 years, in other words, 180 months, you still own this amount, right? You just plug in the number, and then you get this. Okay, so that's another typical example. Okay, questions? Okay, now let's move on, right? Let's see another variation of the same thing. So this is called annuities. So these words are coming from, okay, not from math, right? They're coming from business. So I don't know what it means, so I look at Wikipedia. So it says this, right? So this annuity is a series of payment made at equal intervals, right? So it's like you pay monthly loan or you pay. So example of annuities are regular deposits of savings, saving accounts, monthly home mortgage payment, monthly insurance payment, and pension payments, or something like this, right? So these things are called annuity. So a mortgage is one example. Now we want to look at another example. So the example is CPF. In Singapore, it's more relevant. So when you retire, you give a sum of money, okay, to a financial institute like CPF, right? So in exchange for receiving monthly income for the rest of your life, right? So you contribute to CPF, and then somehow after a certain age, you can get your money back every month, right? So this is, okay, so on the face of it, this is different from the mortgage. But actually they are similar, right? So the textbook claim this is a mirror image of a mortgage, and the same mathematics applies. So why? So you see in the mortgage example is the bank give you money, and then you pay back the bank every month. Now here is a mirror image. Is you give the bank money, you give CPF money, and then you get monthly payment from them. So it's the so-called mirror image. Okay. So you are playing the role of the bank, right? And loaning this amount to the bank who make monthly repayment to you, right? So in this sense, these two questions are the same. Okay. But there are two new things in this CPF setting. So one is you don't determine the interest rate, I, the CPF does. When you take mortgage, the other side determine the rate. All right, so this is different. The other one is the repayment lasts for the rest of your life rather than a fixed period of n years. So I don't think any of us can predict how long we live, right? So it's very hard to do this, to predict. Okay, so we have to sort out these two questions before we answer the CPF example. Okay, so first, how does the CPF decide how long you will live? Well, the answer is very simple. So the CPF uses the average life expectancy as a rough gauge for n, right? So that's the how they decide, right? So for example, if the retirement age is 62, I mean, now probably it's different, I don't know. It changes every year. So, and the life expectancy is 85, then the CPF just expect you have another 23 years, right? So this is simple. You use the average life as a guidance. Okay. So now this part again is completely dependent on CPF. So to determine the interest rate. So the CPF will analyze its various investment to see what sort of annual interest rate it can afford. So usually it take your money and the board of CPF will do their investment, right, to, I don't know, stock market, I don't know what. So the interest rate is calculated based on whatever they do. Okay. So that's how CPF determine the two actual factors. Okay, so after this, so suppose you know the I, you know the N, and then our formula applies because we already said it's the same problem. So therefore, after we get these two parameters, N and I, we can use the same method to calculate the monthly repayment R using this same formula. So this is the same formula. So the first equality only use alpha, only use a monthly rate. The second, the equivalent formula, use both this alpha and the annual interest rate I, right? But they are the same thing. They are equal. Okay? So now let's look at one example of CPF, using CPF as the background. Okay. So on your retirement, you have a lump sum of 200,000 to provide an income until you die. Okay. So the CPF estimate you will live for 20 extra years, right? And assuming it can earn 4% on the capital you give to it, what amount you would expect to receive each month? Okay? So this is the question. Now we just find the parameters, right? So C, the amount of the capital is 200,000, so C is 200,000. Annual interest rate, the capital I is 4%, so it's 4%. The number of years N is 20, right? So then you can use the formula to calculate. But in order to use the formula, you need to find this alpha, right? So alpha can be found using this formula we have seen. So alpha is more or less this number. So once you know alpha, you can use the formula, here. You can use the formula here to calculate. So you plug in these numbers, then you get, roughly is 1,200. Okay, right? So that's example about CPF. Okay. Questions? Maybe you all get bored, but okay. So now let's see the last example of today, right? So then we'll not get bored. Okay, so let's consider this example. It's artificial example, but okay. It is example of what we have covered so far. Okay. So consider this scenario, right? Consider retirement saving plans of twins, Annie and Beth. Okay. So the Anne saves amount $8 at the beginning of each year for 40 years. So at beginning of the year, she put $8, deposit $8. Now Beth will do the same thing, not same thing. She will start 20 years later and saves B dollars each year for 20 years. Okay, so here are the two plans, right? So Anne deposit $8 every year for 40 years. Now Beth deposit B dollars each year for 20 years. Okay? Now, in order for Beth to have the same amount of retirement savings as Anne when they retire in 40 years' time, how much more must Beth save? Right? So now you have you can imagine that the B must be bigger than A, right? So you want to get the same return, because you deposit in a shorter time, so you have to pay more, right? So the question is how much more? Okay. So now assuming the saving grows at the same annual rate, 3%, right? Because everything depends on this interest rate, 3%. So assuming we know interest rate is 3%, we want to know how much more the BESS should pay. Okay? So that's the scenario. Okay. Now again, we are going to use more or less the same formula and calculate things. And okay, so let's try. So let's do the mathematics. So let Y sub k denote the amount of money N has at the end of year k. Okay, so at the very beginning, this is no, right? And then after 1 year, so this is at the very beginning, no. After 1 year, the amount of $8 already in the bank for a year, right? So the N will have this amount, A times bracket 1 plus I. Okay? After 2 years, N will have this, because after 2 years, okay, this amount was in the bank already. Now she contribute another A, because she deposit $8 at the beginning of every year. So at the beginning of the second year, she contribute another $8. So this amount was in the bank for another year, for a year. So with interest, you get at the second year, N has this amount. Okay, so now you somehow multiply this out, you get this. Okay, and then after 3 years, the same logic applies. So the Y2 was sitting in the bank for another year, and N contribute another $8. So you have this amount sitting in the bank for another year, so she deserves this amount times the interest rate, 1 plus the interest rate. So it's this amount. Now if you replace Y2 and then you get this. So you see the pattern, right? So here is a geometric series. 1 plus I, 1 plus I squared, 1 plus I cubed, and so on and so forth. Okay, so by repeating this or iterating, you can get Y sub k. After k years, you would get A times, it's like this, A times the sum from 1 plus I squared, all the way to 1 plus I to the k, right? So it's a sum j equal 1 to k, 1 plus I to the power of j. Okay, using the formula, you get this. So this is I, this is not 1. This is a capital I. So you get A times this. Okay. So now after 40 years, if you plug in the number, so you have A here, and this is, I don't know, 3%. L is 3, right? L is 3%. So after 40 years, N has this amount. Okay. Now, similarly, for BESS, right, it's the same formula almost. So it's the same interest rate, but it's shorter. It's 20 years. Now, every year she put B dollars. So at the end of this period, BESS would get this. Okay, so I skipped the calculation, but it's exactly the same. So from these, okay, if you equate these two, right, because we want to say, suppose they want to get the same return, how much more B should pay, BESS should pay. So let's set equality between these two terms and move things around. Lots of things are canceled. So you get B over A is more or less this, I don't read the term, right, over the other one. Now, if you plug in calculator, you get more or less 3. So, in other words, she has to pay 3 times more than her twin sister. So three times was quite a big number, right? So therefore, the message of today is you should prepare your retirement early, like now, right? So, okay, so that's the end of the first lecture. Please do give me feedbacks, whether by email or talking to me, okay? So somehow I miscalculated the time, or because we don't have a break, right? So maybe next time I'll try to cover more, okay? So we'll use a 1 hour and a half. Okay, so hopefully see you on Friday.